just were born, there were multiple claims of exoplanets, which turned out to be some combination of bad astronomy and bad data analysis. And whether you realize this or not, this actually had a pretty important effect on our field. And that is because in the 90s, when we started discovering planets in earnest, there was a strong sense of paranoia. And so it was interesting that they combined what we might call relatively simplistic statistical methods with their great paranoia to produce good science with robust actions. Now, subsequently to that, we had some rapid progress as radial velocity surveys found many more planets, primarily using frequentist methods. We saw some early population analyses of radial velocity surveys, and then as transit started coming into, branched out to exoplanet atmospheric characterization. Some of the early work on correlated noise, I'm sure it was seen earlier, but I remember sort of it hitting me how important it was from a 2006 paper from Frederick Pont. We had some beginnings of the claims of planets that now are sort of regarded as dubious and been cast into doubt. And in some ways, we've lost that paranoia we had early on. And I think that that's a little bit good. It's good that we're willing to go out and push the data to its limits, but it's also been a little bit negative in the sense that our field, both as an ambassador to each other scientists, and also to the broader public about representing all of astronomy and indeed perhaps all of science to some people. But I think the danger of maybe overstepping the limits of what the data support is real, and so we should keep that in mind as we try to push the limits of technology, but also stay grounded in claims that will stand the test of time. So on the positive side, there's also been a lot of progress. I sort of first became aware of Bayesian methods being applied to exoplanets in the run-up to preparations for the SIM, the Space Interferometry mission. It didn't actually happen, but nevertheless, people developed a pretty nice framework for trying to perform a Bayesian analysis of both the observations, but also adaptive design and how the survey would be built. Then we saw some pretty rapid improvements in Bayesian methods for characterizing masses and orbits of planets from radial velocity surveys and also transit parameters. And it's at the point where now most any radial velocity system where the signal is dominated by dynamical effects, it's basically easy to solve in the sense of if you have questions about it, find someone who's done this before, and it's basically a solved problem, the parameter estimation part. One thing that I was very pleased about was that looking back on it, I tried to figure out the microlensing community. There's sort of a disadvantage because everything has to be statistical. But on the positive side, they were sort of forced to think statistically of their data from the beginning. And that's because I think they've done a very good job. I was talking on a plane with Dave Bennett, and he hemmed and hawed a little bit, but he basically agreed. They didn't embarrass themselves with false claims. And that's pretty good for a field getting started any time. Inevitably, the early data is challenging, and making sense from the beginning, I think, is very impressive. We've also had a pretty good success rate with some of the Kepler analyses of multiple transiting planets and triple stars, where you have interactions there. And just now we're beginning to see hierarchical Bayesian analyses of exoplanet populations, particularly the Kepler data, but other samples as well. Direct imaging comes to mind. So I thought I would highlight a few what I'll call success stories. We already mentioned that Bayesian estimation of orbital parameters from Doppler surveys with the signal is dynamic was basically routine. It often is done by people who don't specialize in statistics. They've gotten to the point where it's now relatively straightforward. That being said, there are some cases that are a bit more challenging. I highlighted these not because I wanted to be sort of a jerk, but if there's anyone who knows of a strongly interacting system which hasn't had a proper analysis and it's worth doing, please let me know, because I think we'd be anxious to try to cross all those boxes off. Some I haven't did because at the time the data wasn't public, but maybe it's public now and I just didn't notice. So I think it's very nice that we're able to combine, say, our radial velocity observations, orbital dynamics, and statistical methods, and study these systems that are very rich because of their interactions. Another thing that I think we've seen a lot of progress towards is coming up with these methods for having an established criteria to distinguish the correct number of planets based on a given data set. As Suzanne mentioned, it's not a solved problem. There are still certainly people using different methods, sometimes more or less rigorous, sometimes more or less effectively. But nevertheless, we've seen a lot of progress towards that, and I encourage people who are interested in a problem or a data set where they want to do as good a job as possible to talk some of the people who have experienced that in this room and the field a bit broader. We're now in quite good shape and have a bunch of tools. They're not always easy. It's not a nice wrapped up black box, but there is a lot of expertise in that, and we've made a lot of progress. And perhaps the biggest success is that if we ask what's the limit of radial velocity surveys, it's no longer either the instrumentation nor the statistical method. So we've really pushed both of those to the extent where we're limited by stellar activity, astrophysical noise sources. And so I think that's both a great thing in the sense that we've reached quite far along. It's also a bit of a challenge in the sense that now we have new challenges of understanding stellar activity, which I think will keep us busy for quite a while. As an example of one of those cases of characterizing a strongly interacting planetary system, I'll highlight some work on GG876. Victor Nelson will have a poster on this later in the week. And here there's a system, originally 2 planets near 30 and 60-day orbital periods. A bit problematic because of the aliasing sort of mass sprayed the inner planet and perhaps an eccentricity term the outer planet. They interact so strongly, this was clearly recognized as 2 distinct planets. Later they found an interior planet that's causes a very rapid dynamical timescale and makes the modeling of interactions very computationally expensive. And then there was most recently an outer planet around 120 days. So these planets participate in a 1-2-4 mean motion resonance where the inner planet goes around 4 times, whereas 1 time the outer planet goes on. This creates strong planet-planet interactions, whole systems processing once every 9 years. That allows us to both detect these interactions and use them to characterize the resonant interactions, the secular interactions, the inclinations, all of which provide clues to the formation history of this very nice system. So that's one example of the state where we are in terms of characterizing strongly interacting multiple planet systems from radial velocity data. We can do a lot of cool stuff. Stellar activity is becoming increasingly a challenge for these methods, such that we have to ask ourselves, is the statistical model we're using for our observational uncertainties actually reflecting the true sort of process generating our data, or is there additional astrophysical issues that we need to worry about? And so one of the things at the recent Precision Radial Velocity meeting we had was a real push for that we not only have to have a correct statistical model, but we have to understand what it is we're modeling, and we don't have a physical model anymore. So we need to first characterize what is the model that generates stellar activity, what is that based on a lot of observations, both high precision, high cadence, high frequency, so that we'll be able to perform these analyses of stars with activity to first understand what is the basis for understanding their activity and distinguishing that from planets. I think we're going to switch from getting lists of times, velocities, and uncertainties to reporting a lot more information. The vectors they take are very rich. There's a lot more information, some of which can tell us about stellar activity, and we need to figure out which are the best ways to summarize that information, make it accessible for statistical analyses. And then combine those with principle design and tested and validated statistical frameworks. So their results are not just sort of one person's ad hoc analysis, but really something that the community can test, reproduce, tinker, test the sensitivity of, and really bolster the understanding of claims of planet detections in our field. So some of the things that I've noticed that the community needs to sort of be pushing towards is trying to not just apply a statistical method to a data set, but to first test the method on simulated data. In the case of active stars, that means including simulated stellar activity. Not easy, not something with the perfect model of, but nevertheless, it's a whole lot better to know your algorithm works on simulated data than to not even know if it can correctly analyze data from the exact model that you're using to analyze it. So I think that's really critical to at least validate your methods, and ideally also to verify them, to be able to apply it to astronomical data, not just of one data set where you're looking for an nth planet, but also other data sets that have perhaps less planetary signals and therefore are accessible for testing the outputs of your models on realistic noise sources. So sometimes we use iterative algorithms, whether it be Markov chain mining Carlo or nested sampling. And I also see in the literature more emphasis on establishing the convergence, or at least a test for non-convergence that has been performed on those analyses. And also testing the sensitivity of results. Things like you're going to have a choice of priors or a stellar activity model. How sensitive are your conclusions to those assumptions? And this is not always trivial for astronomers. Sometimes it's challenging enough that it'd be wise to involve experts in statistical methodology, and it's great to have some of those folks here this evening. Okay, so that's for the radial velocity highlight section. Now I'll move to middle portion talking about transit time variation, something near and dear to my heart. We've had a lot of interesting work from Kepler, returning observations of short period systems where you have tightly packed planets, called these STIPs, systems of tightly packed inner planets. And they're able to characterize the masses and orbits based on these transit time variations and also improve the stellar properties that then translates to improved planetary properties. The basic premise here is that when you have one planet orbiting a star, it serves as a clock. You can set your clock literally by the times at which the planets transit the star. Once you have multiple planets orbiting the same star, then you're able to have the interactions cause the planets to hug each other earlier and later and accelerate and decelerate the planets in their orbit so that you see deviation of transit times. So the movie got reinserted to the plays, they could start at the correct start times. Whoops, didn't notice that one. The first case for planetary analysis that I really like, the joint photometric modeling of the Kepler data, the dynamical modeling of the orbits, and the statistical modeling as well was for Kepler 36. There have been a few other systems where we hadn't yet employed the full Bayesian framework. Kepler 36 is notable because the star also has astroseismic constraints. So in addition to measuring all these transits, you can see each planet has a nicely measured transit. Sometimes there are different depths to the different two planets. And then once they target the star for short cadence observations, much denser sets of observations, able to get even more precise measurements of the transit times from those. Turn those into constraints on the various planet masses and orbital properties. It is actually just a subset of properties from that analysis, not to worry about which parameters what. The main thing to realize is that sometimes transit time measures something that might not be what you wish it would measure. And that comes across as these highly correlated parameters, and as a result, some of the standard techniques we've been using were very inefficient. We need to switch to differential evolution, Markov chain, Monte Carlo to be able to deal with those strong linear correlations. Unfortunately, that's not all. There's also some sickles and bananas and other nasty shapes that caused even this method to be relatively inefficient. So it took a lot of computer time to reform what's one system and now a subset of that data. So this highlights the need to improve the efficiency of the methods we're using to do parameter estimation, these strongly interacting systems. We've made some progress on that. I think there's still room for lots more. As I mentioned, this system is special because the star has astroseismic data, and you can measure the star properties very well. For most of these systems, the precision with which we measure the planet properties is limited by the star properties. And so because the star is measured very well, we also got nice constraints on the planet radii and densities, shown here in red relative to some of the other measurements at the time. I'll skip ahead all the way to one of the more recent transit time results coming from Kepler 138, also known as KY 314 for people who've been studying it for a while. There's, again, 3 planets packed really closely together, close to their host star. The inner one's quite small, but the media likes things like that. We can say a Mars-sized planet. I also find interesting here 2 planets that are very similar in size to the Earth, 20% larger, at orbital periods that are pretty comparable, both of 14, 24 days. And as we'll see, by measuring their transit time variations and then analyzing those, we come to the conclusion that their densities are quite different. So the mass of those 2 planets, 2 Earth masses, 2/3 of an Earth mass, wildly different, implying different densities, even though the same star, the same formation, very close orbital periods. So a bit of a puzzle there for the formation experts. Also, the outer plane is the less massive one, breaking the trend in some of the previous systems that have been analyzed where that inner planet sometimes is a bit less massive. Now, for people who read the abstract very carefully and they pay attention to error bars, a few people ask, well, you really know that. The error bars, I noticed the 2 planets overlap. That's sort of true. They do overlap if you project first to ask what's the mass of each planet. But remember, for these transit time variations, we often measure ratios better than the actual parameters themselves. For example, if we look at the mass of the 2 planets, say mass of planet C on the horizontal axis, D on the vertical axis, you'll see they're very highly correlated. And so we actually do measure the mass ratio quite well and clearly exclude the possibility that the outer planet is less massive than the inner. So there's a very nice, strong constraint on this planet's mass ratio and its density ratio, despite the uncertainties in both the star properties and the overall sort of scale of mass in the system. Just for fun, a nice little video comparing the progress we've made in the mass radius diagram. The blue points, low density giant planets, the yellow points, high density, presumably in many cases rocky planets, and sort of zooming in and then highlighting these recent finds as we push the limits to lower masses and smaller planets. Now, one type of planet that we haven't seen a lot about yet, but I think it's going to be quite puzzling, is highlighted by the Kepler-79 system, KY152. This is another system that's in one of these resonant chains. So the orbital periods of the planets, in this case, 1, 2, 4, 6. So 4 planets, even more than the Galilean moon system. Pretty fascinating. Orbital periods ranging from weeks to months. And planet sizes going from, sort of Neptune-ish sizes all the way up to giant planet size. The planet out at 52 days. And so what's interesting with the system is the transit timing variations indicate that one of those planets has a small mass, but a large size. And so sometimes when people plot this, they sort of zoom in on the lowest masses and lowest sizes, and they leave out some of these low density, high radii planets that are a bit of a puzzle to understand. And it turns out, even though this is at the moment sort of the strongest one in terms of the published values, it's not alone, it's not isolated. Daniel Yonta-Putter has been analyzing this in other systems, and we can see that there's several systems which have clearly much larger radii than you would expect from a rocky planet, even though their masses are quite small, so several Earth masses type regime. So how did these planets form? It's a bit puzzling. It's relatively easy to imagine a high mass planet has a lot of gas. How does a relatively low mass planet have enough gas to cause the radii to be that large? That's a bit of a puzzle to think about. One of the other questions that comes to mind is, well, why haven't we seen these planets before? Why are we only recognizing them now? And in particular, radial velocity surveys and transit timing are very complementary. So here's a figure showing the Kepler planet candidates as sort of gray points, and sort of the periods and radii like you're used to seeing. And the colors indicate in green the radial velocity measurements, in orange the transit timing measurements. And what you can see is that they're slightly offset populations. Radial velocity surveys are most sensitive to the closest, smallest orbital periods and high masses. Transit time variations are more sensitive to planets at longer orbital periods and a bit more precise times, and the radii are a bit larger. And so there's an offset. The most precise transit time work comes at sort of weeks to months, and the most precise Doppler work comes at orbital periods of days to a week or so. So there's perhaps a difference in the population that's being studied there, also in the way they're targeted. So transit time variations and sort of take what we get when there is a system that has strong transit time variations and what exact properties it has is a little bit of luck. With radial velocity surveys, they normally target systems that they're particularly interested in. So they might, for example, say, let's go look at the mass of small planets. And many of the planets for which the Doppler measurements have given us a mass of a Kepler system were part of sort of really intentionally targeted small planets, and they went and measured their masses. If the density was low, they wouldn't have been able to detect it. If the density was high, they would. And so that creates a sort of complement or a different type of bias with two data sets. And so I suspect that there are very well difference in these two methods, but also a difference in the two populations being studied. So at these very low masses, perhaps there's a population of planets which, if they had been closer in, processes such as tides and irradiation, X-rays, photoevaporation may sculpt those low density planets and erode much of their atmosphere. So it's important that we not only understand the two detection methods and how they sculpt the populations, but also to understand the physical characteristics of these potentially different populations. So there's several challenges for transit time variations going forward. I already alluded to increasing the efficiency of posterior sampling. In particular, many of these analyses, most of them have been sort of one system, one paper, months or years of work from a group of multiple people. We're getting a little bit better, as I mentioned. We're sort of trying to analyze several systems in one shot now. as we make a little bit of progress, but nevertheless, efficiency is still quite a computationally and human-intensive process. We wanted it not just to sort of ratchet up the rate of discovery, there are hundreds of systems sort of waiting to be analyzed, but also because we sort of know in the back of our heads, there's also cases where not all the planets transit. There's been a few of these that have been analyzed in detail, where they are able to measure properties of the systems, in some cases even infer the mass and orbit of the non-transiting planet completely, because this data set is so rich. But for every one of those, there's typically many more where the information is less constraining. And as an example of that, the Kepler 50 system here, there's 2 planets that transit, and if you look at the transit time variations, maybe you don't sort of notice this little dip in the, or deviation in the red planet's transit times, but it's pretty obvious that the planet C here is nothing like the model. A 2-planet model simply fails. A 3-planet model works. Okay, great, we have 3 planets, we're all happy. The only problem is another 3-planet model works and another 3-planet model works. So it's a degenerate case where we have many different local maxima in the posterior distribution, each corresponding to a significantly distinct model for that outer planet. Nevertheless, we were very pleasantly surprised to see in our preliminary analyses that the planets B and C actually are fairly relatively well constrained in terms of their mass, despite humongous differences in the mass and orbital period of the non-transiting planet. And so this may be a sort of interesting application where, in order to correctly characterize these 2 planets, we really would like to perform a robust posterior sampling from a distribution that's very poorly constrained in the parameters of this 3rd non-transiting planet. So that's a key reason why we need to increase the efficiency of these sampling algorithms, not only to just do things faster, but also to enable analyses of these more complex systems that are much more challenging. Another goal that the transit timing community needs to work on in the coming years will be sort of testing the robustness and sensitivity of these TT mass measurements, effects like correlated noise. On one hand, the beauty of this technique is it's all Keplerian dynamics. There's sort of nothing that can go wrong, right? It's so nice and clean. But then you start scratching a little bit like, well, okay, that correlated noise, what does that do to me, right? And so one thing that Daniel said was to look at the distribution of residuals of transit times that were measured in systems where we don't expect there to be large transit time variation. So we go through all the multiple planet systems, start the ones where we predict there should be a big signal, and only look at the ones where we know of nothing that would cause transit time variations. Now, it may be that there's some unseen planet that is causing a little signal, but that's true in most any other data set we analyze. There might be some undetected planet that's causing a little bit of a signal. And then you can compare the green curve here are the residuals of these thousands of transits, and then the dotted curve, which you particularly see out beyond 2 sigma here, is a Gaussian model, and you see the Gaussian model grossly underpredicts the frequency of events out, say, 3-4 sigma. Interestingly, we found that a T distribution can model this relatively well, and we're beginning to use that as a way to test the sensitivity of our conclusions to the assumption that the measurements have a Gaussian distribution. What if we allow for a T2 distribution of their timing uncertainties? So that's one approach to solve this problem. The other is to actually try to model the light curve itself better. And here I'll show some work from Rebecca Dodson, who's been looking at using correlated noise models for the light curves. And you can take a typical Kepler light curve and you can just like eye see the various correlations, presumably stellar activity causing nice large variations. Then you zoom in, you can see even on relatively short time scales of days, there's still correlated noise. And the typical way we've dealt with this in the past is fitting some local polynomial around each transit time and then fitting a transit model to the deviations of that local polynomial. And so what Becky did here was she considered both a model where she put in Gaussian noise for the model, but also one where she allowed for a red noise component using a Gaussian process model. And they compared what's the estimate for the amplitude of the noise in those 2 cases. And what you can see is that the amplitude of the stochastic component of the noise is about 1/3 higher when you assume it's all white noise, because you're attributing some trends to randomness, when in fact there's a correlation. So what this means is that A, there's the potential to improve our sensitivity if we properly account for these, and that B, there's a potential bias if we don't properly account for these. In particular, when we're doing transit time analysis, we wanted to see how well we're measuring the transit times. So she's began injecting simulated transits into light curves where there's not a not a planet actually transiting, but she knows the exact time she injected, and then can fit a transit model to it. And then from that, you can make a histogram of the times you recover if you assume either a white noise model or a red noise model. And in the white noise model here in black, you can see that the histogram is a little bit offset, but okay, that should happen all the time. It'll be offset a little bit. And then the dashed red curve here shows the result using a Gaussian process, that's likelihood. And then this can be repeated. Okay, for I, we'll keep it down. But you can see sort of by eye is oftentimes using the correlated noise does cause the distribution to favor the true transit time more than the white noise model, in particular when you have a bimodal likelihood. A case like there, it's a pretty substantial difference. To sort of quantify this, you can look at what percentile of the transit, the true transit time followed, what percentile of the posterior distribution does the true transit time lie at? And so it should be a uniform distribution if everything were perfect. What you see is that for most of the transits, things go very well. But as you get sort of the 90-ish, 95th percentile, you begin to see pretty significant deviations if you were to ignore this correlated noise. And so what we're hoping to do in the near future is to combine these methods to be able to provide more accurate measurements of the transit times and their uncertainties to fold into our dynamical analysis. And then I think the next big challenge for transit time variation studies will be modeling the transit time variation population. So there we have a nice population of objects coming from these surveys, hundreds of systems where we have significant signals. We expect there to be about 150 to 250 nice transit time signals. Steve Mazzo led the most recent TTV catalog, and in it he finds 199 systems with sinusoidal TTVs. Pretty nicely in the middle of that estimate there. And for these systems that are near first order resonance, the signal is nearly sinusoidal, and so that's easy to model. And then we can look at the distribution of those transit timing signals, and you can see that there's hundreds of systems and are amenable to such analyses, and there's only dozens that have actually received sort of published analysis. So we still have a long way to go in performing these. There have been some initial population models. People looking at either the transit timing population on sort of the near resonant systems or the published systems. These are nice steps in the right direction, but still a long way to go. In particular, I think it's very important that we analyze all the systems. If we restrict our attention to the systems that have been published or the system where there's a detection, clearly that's going to bias the population. So there's a lot of work to do. I list several of the key elements here. In the interest of time, I'll just say that we're beginning to make progress. And so picking what we think are the most important aspects, tying this into a hierarchical Bayesian model to constrain the planet mass and radii. Here's sort of the input data, and then turning that into constraints on the mass radius relationship and eccentricity distribution of these planets. In this case, we're using a model that allows for two different populations, one population of low eccentricity planets, one population of high eccentricity planets, and then we can characterize the distribution for the fraction of each component. Here are the right-hand sides, then the eccentricities distribution of each of those components on the left two columns. And then we look at the posterior predictive distributions. One thing that's really fascinating is they don't look to the eye that much different than a simple one-component model. But when we do the parameter inference, if we don't include the potential of that second population, it can significantly bias our inference of the population, the eccentricity dispersion of that low eccentricity component. So even though it's sort of things that by eye look like they're relatively small, because these distributions fall exponentially at large values, if you don't allow for there to be this higher eccentricity population, it can really affect your inference for the low eccentricity population. And so I think one challenge for various population studies, whether it be transit time variations, rate of velocities, Kepler, and so forth, we're tying together information from potentially distinct systems, whether that's because of the way the systems were chosen to be observed or the various detection limits of the two different methods. We'll be able to perform each of the analyses independently, but there'll be a bit of a challenge sort of tying them together and combining those populations. And so we'll see that both in the mass radius relation, also the eccentricity distribution, multiplicity of issues as well. So I think there's a lot of room for improvements in the analyses that we're doing. And I thought I'd return back to the big picture questions. So what are some of the ongoing challenges in exostatistics? I mentioned earlier, I think it's important that we provide not just a method that a few experts can solve the Bayesian evidence for an nth planet system, but really to have robust estimators that the community accepts the whole and are accessible to astronomers who want to perform radial velocity analyses themselves. It shouldn't be something that they view as black magic. We need to make it sufficiently trackable and intelligible that they can understand what you're doing and have confidence in it. As we progress forward, disentangling radial velocities and solar activities will become increasingly important as we see that often the systems have solar activity at a level equivalent to or even larger than the Doppler signal. We've seen, I've already discussed the challenges of Bayesian analysis of transit time variations, and a little bit of the challenges of hierarchical modeling, which we'll hear a lot about on this meeting later, so I've been relatively quiet about. Then the last two areas are actually probably some of the most interesting things to do in the coming years, but also the least useful to say about them. Atmospheric characterizations in dire need of improvement to their statistical approach so that they can have robust results that can be believed by their own community and by the astronomical and scientific community as a whole. A lot of really exciting results will inevitably come of these, and I think it would be great if the experience is being built up in these other exoplanet subfields to help improve that as rapidly as possible. And then we heard about direct imaging. Several programs are coming online, either have come online or in the near future. ALMA, microlensing, they'll be first. There'll be lots of new data. Okay, it's not really completely new, but it's relatively new in the sense of the quality and the abundance of it for exoplanet work will be relatively new. So I think we have an opportunity to try to help those subfields transition performing sound statistical analyses as rapidly as possible. And so I thought I'd leave a bit of a charge to the people in this room. All models are wrong. Some models are useful. This is a very important thing to keep in mind because sometimes we choose to use simplified models. Simplified models can greatly aid computation. They can make it easier to understand what our results sort of mean, but they can also be terribly misleading. We saw that in the case of if we ignore the possibility of red noise, if we ignore the possibility of there being two components in the eccentricity distribution, two populations in the mass radius distribution. All those are examples of where if I use too simplified of a model, I come to wrong conclusions. On the other hand, complex models can be really painful and totally impractical to compute anything you actually care about. And they can be a pain even once you compute it. You can't make sense of a 52-dimensional parameter space. What do you do with it? Both of these are challenges to work with. And our challenge as scientists and as statisticians is to find a useful balance, a model that's simple enough to understand what we mean and to capture the essentials, but complex enough to make sure that we really are capturing both the things that are essential to because they're there and essential because they might be there and we don't know if they aren't. And so being able to strike that balance of simple and complex models is very difficult. In the end, you don't know you have the right answer. And so I'd like to see our field make progress towards providing robustness tests or conclusions. When we have a key conclusion, does it depend upon the model we assume? A really basic first-order question that we should be trying to address. And so I'd like to see us do a little bit better job of trying to apply multiple statistical models to our data in order to determine which of our conclusions are robust to that. And then finally, I thought I'd point out as a congratulatory note the history of ExoStats meetings. It appears that there were very few, maybe a few sessions or something in the early days. 2006, there was a semester-long SAMSI program. Joe mentioned SAMSI is one of the key drivers for integrating statistics and applied mathematics with many fields. One of the things that I thought really came well out of that was developing estimators for Bayesian evidence of RV data, both testing existing methods and developing some new ones that are now being applied. So that's one example of what can come out of these. There's a series of statistical challenges in modern astrophysics. It's mostly other astrophysics, but it has had some exoplanets in the past, and I'm hoping that in the future it will be even more so. There was a 3-week SAMSI program that had several working groups that did a lot of good work, and then a follow-up meeting last summer at CMU, ExoStats 2014, and now it's reached the point where it's the IU focus meetings on. So we've seen sort of really great growth in this area. People recognize the importance and filling the room for sessions on this. So I'm really encouraged to see that. And so I'll just leave with 2 upcoming meetings. The Statistical Challenge of Modern Astrophysics next summer. I think will be a great venue to get some of us back together and report on our progress. And then for people who really want to engage with statisticians for the long term, this SAMSI program called 16 Spring 17 There's an opportunity to form multiple working groups. You don't have to be there the whole time. You can participate via telecon for part of the time. You can get a subgroup of people to come for a week or two and focus on one particular problem. So if you're interested in helping to pick an area and formulate a working group and organize, I hope you'll talk to some of the people involved with that, Jogesh, or some of the other folks here, myself, Eric Feigels, I'm sure can also help get those messages to the right people. With that, any questions? I just turned on.
Okay.
Thank you for that overview. You mentioned correlated noise. It seems to me you're missing the effect of the transit shape variations when you do the TTV measurement. Aren't you assuming a constant transit shape? And if so, what's the effect you expect? And wouldn't it be better to just go to a full photodynamic modeling the whole thing?
Okay, so the question was related to, is it wise to assume the transit shape is not changing? So in most cases, you can work out what the expected change in shapes are based on dynamics, and it's very, very small. So in most cases, it's a very good assumption. In some cases, where I come from one end, there's information of duration gradually showing a change. And so in those cases, yes, you're right. You would want to have a model that allowed the durations to change. The most sort of the best way to model is the whole dynamics simultaneously. Sometimes that's necessary. I know some papers don't work where they're doing exactly that because of these issues. Other cases, it's maybe practical to say put in just a duration derivative. Let's say a gradual recession over the course of the 40 years. So yeah, we have to always be aware of when your model has approximations, and keep in mind when they're valid and when you need to allow for additional help.
Any other questions? There's one question, gentleman in the blue shirt. And then there's another one at the back.
One of the things you talked about is that sort of like publication, there should be some like text that are showing that you want to conversion the iterative processes. But I was wondering about was sort of in that same sort of vein, how much should be included in the publication that uses iterative processes, specifying some parameters in such chain language that specify this, so that isn't just clear what you did in a conceptual level, but also that's a structure.
Yeah. So I think probably the best case scenario is if the posterior samples were available. If someone really cares, they can go and test for themselves whatever test they want. The good part of that is that someone may want to apply your analysis in a context that you didn't anticipate. So they will have some prediction for an imaging campaign, and you were thinking imaging, and so you didn't test whether the angular separation was well established. So there may be cases where that's sort of the best mechanism, or perhaps having code the whole thing is reputable. But of course, not everyone's going to invest the effort to go look at your posterior sample and do checks from that. So I think also providing some summary information. I mean, if it's a simple problem, it seems a little bit silly to show things like trace plots when it's pretty clear, but nevertheless, what we have to realize is that it's clear to us because we spent the last 10 months of our life doing it. But to the reader who hasn't ever seen this before, they don't know that. And unfortunately, sometimes there are issues. In particular, we don't say something is converged, we say it's converged well enough for some purpose. Right, in the sense of if I'm interested in the interquartile range, maybe a 10,000 link chain is great. But if you're interested in 99.9 percentile of something, well, that same chain may be totally inadequate. And so it's not a yes/no thing, and that's why I think it's so important to provide diagnostics so people can make assessments of what it's useful for.
There's another question at the back.
And I'll also make a plug for archive ancillary tables. So if someone like Nature says you can't have any more tables, Archive lets you upload extra tables, figure sets, and then we can find me if Nature's grumpy about it.
So I was interested in your slide when you said the early days were more conservative and now perhaps more optimistic. But in the early days, progress was fairly slow and now it's very rapid. So does the field progress faster if we're more willing to publish less robust, maybe more marginal detections?
That's an interesting question. So there's many confounding variables. So of course, there's many more people working in exoplanets now than there were 2 decades ago. So I think that at some level contributes to the higher publication rate. I think it is true that just because something isn't a 7 sigma result doesn't mean it shouldn't be published. I think that if you have a marginal result that's interesting, it's totally appropriate to publish it as here's a marginal result. And sometimes that can be done effectively. Unfortunately, no matter how well you word your abstract, sometimes those words are going to be twisted. Maybe not intentionally, maybe intentionally, I don't know. The media often doesn't read much beyond the title, let alone or abstract or something. So I think particularly if you know there's a result that's likely to get broader attention, it would be wise, I think, to try to make an extra effort to try to couch in a way that we don't sort of look bad to others, even if section 7.2.4 said that, well, we can't really tell this from activity. It's an art. I don't have a solution, but I think it's something we need to be cognizant of.
Okay. So we have time for one last question if there is one. And otherwise we'll move to our second speaker, who's Prof. Jim Berger. He's a very eminent statistician